Yeah, I guess I'm going through loud and clear. Yeah, so my name is Simon. Let me just start out by saying that I'm very excited about being here. There's been some very nice talks. I'm quite excited to, coming all the way from Denmark, Copenhagen, to talk about what it is we do at our research institute and how that relates to this, a bit provocative title of bringing high performance to Python NumPy without changing a single line of code. So I'm just going to start out by setting the scene of what I actually mean about high performance and why it's interesting not to change as much as a single line of code. What's really the motivation behind that? So the thing is, we got this guy. So you probably know him, maybe perhaps not by the picture, but he's very famous for Moore's law, stating that the number of transistors on integrated circuits doubles approximately every 2 years. Now, this has been a very good thing for performance because it used to mean that we would get double the performance every 2 years without doing anything. We just got faster and faster processors. But somewhere around the Pentium 4, if the trend had continued from that point on, it would have meant that the core temperature of the CPU would have the same surface temperature as the sun has today. So we have actually hit what is called the power wall. And you can't really scale performance on the single core by just adding more transistors. So how to what are you going to do then? So the ones designing processors have made a lot of different approaches. And one approach is using instruction level parallelism. The Pentium 4 has 34 pipeline stages, and they can do speculative instruction scheduling on that. But the cost is that they spend most of the real estate on the CPU for doing branch prediction and doing caching. And actual computations, that's not really done on the CPU anymore. Most of the real estate is actually used on, not computing, but setting up computations. You need to climb that wall. So what do? So you can't really scale your computations on one CPU, so you need more CPUs. And then you have to get more performance, you have multi-core systems with shared memory. And you have tile-based architectures. So the regular x86 architecture only scales from somewhere between 1 to 8 cores on something like our laptop. Then you have the Opteron processors, which is 1 to 64 cores. Then you have these tile-based architectures, where you have a lot of computing tiles set up in a grid. And you need a completely different programming model for that. And then you have the many core architectures, such as your GPUs, which you can use to get high performance computing. And then finally, a very exotic thing today is FPGA programming. So to be able to compute and optimize your hardware for a certain task. So why was all of this stuff interesting? It was because we needed to get high performance, and those actually building the processors have some issues about how should we use the transistors to do computations more efficiently. And they are providing these different architectures for us. And what we as the programmers do then is instruct the hardware in a thread level notion of doing your computations. And then we do computational clusters, or we do distribution in various ways. And it's interesting to do these things because we need high performance computing. I mean, for my parents, it doesn't mean much whether their open office application opens in 3 seconds or 20 seconds. But when you're in the game of high performance computing, you're doing simulation. It might mean that your computational fluid dynamic simulation runs in a month or in a day. So when you're in this game, hitting the performance wall really hurts. So that's really the key motivation. So how do we do this? There's been a great lot of talks about how you do high performance computing today in Python and how we're supposed to do it further on. So today the approaches include NumPy and PyCUDA and PyOpenCL if you want to utilize your GPUs. If you want to do like your regular shared memory system, you're using NumPy, then you use multiprocessing to distribute onto your cores. Then you start to use MPI for Pi, or PuppyMPI, the not so famous version of MPI, to distribute onto your network. And you have some great tools like NumExpression and Weave that can optimize your expressions to make those go faster. And you have Theano, you got Cython. There's a lot of tools that builds upon NumPy and Python to get high performance. And the list really goes on. But the problem is that it's an entanglement of your high-level productivity NumPy code with low-level instrumentation. And at least for the applications at the Niels Bohr Institute, we really don't want the physicists to be parallel programmers. We want them to think about solving problems in their physics areas. We really want them to be physicists and not parallel programmers. Because the thing is, it's not easy, it's not trivial to do all these things. It's not trivial to do the low-level instrumentation, which is what you need to do today to get performance. So that's what we want to do. We want to don't write a single line of code which is low-level instrumentation. We want everything at the application layer to be close to what the physicist needs and what everybody else needs in terms of the application, and they shouldn't worry about low-level instrumentation. So that's the idea. But I'm not Harry Potter. I don't actually have a magic wand. So what are we going to do? So to realize this idea, I should say that it's a research project that we're working on, and we thought, okay, so how are we going to do this? We thought, okay, if we can't do it at the application level, we need to do it at some other level. So let me introduce to you Copenhagen Vector Bytecode. Copenhagen Vector Bytecode is a system for automatic runtime optimizations and parallelization of vectorized applications. So we're not trying to solve all problems. We're not trying to do high-performance computing when you load up your LibreOffice or OpenOffice. We're interested in a subset of applications which are the vectorized applications. So usually your applications in linear algebra and when you use numerical Python. And our approach is we do this at runtime because there's a lot of neat information when you're doing stuff at runtime. So I've made this neat little graph here. So the idea is we want the separation of concerns. So at the top level, we have what we call the front end. And the front end consists of some language. That could be Python. And then you have your language bridge. And the language bridge is the thing binding the language to our runtime system. And that could, for instance, be hooking into numerical Python, instructing numerical Python to use our runtime system. And then down in the actual system, we got these things. We got these things called vector engine managers. And the managers are the suit and ties of the system. They're the guys who are scheduling stuff. They're taking instructions and the high-level notion of computations, and then they're telling the workers down here, the engines, to do the computations. Let me further that example. So you got like Python NumPy up here, which translates the regular Python in your NumPy code into what we call vector bytecode. Now the vector bytecode is something that you should just think about as a very simple assembly instructions, like an add of two operands into a third. So we got something like doing an add, but where the operands are vectors, not registers. So it's like a high-level vector bytecode on these operands. So at the top level, you got your language and your language bindings. We transform that into something that's similar to this. And then that code is pushed into our system. And at the top level, the idea is that you have got something like a suit and tie for managing clusters. So that guy is going to look at, so who do I have available? Oh, I have all these nodes. So he looks at the vector bytecode and then he says, okay, I'm going to distribute this onto these nodes. And then the nodes, when they get the bytecode, they say, okay, I got the code. Now I'm going to run this on the GPU. I'm going to run this on my 8 cores that I got available. So the idea was to separate the concerns, and we've done that by having this intermediate language. And Python NumPy is just one way to do it. There's other ways, other languages where you really want to have high productivity close to your domain. So you got stuff like IDL, the interactive data language, and you got the domain-specific languages for doing exactly what it is that you want to do. And the idea is that you write your bindings for those language and translate that to vector bytecode. For those of you who saw the number thing from Oliphant, it's kind of related to that. Our intermediate language is just not LLVM. It's vector bytecode. All right, so we had the separation of concerns, and we tried to design a system that works in this hierarchy. So the tricky part was actually trying to implement it to see if this idea could actually be realized. So we did that by implementing a Python Numpy bridge and then implementing a couple of engines. So let me start out just briefly going through how we implemented the bridge. So it's actually kind of simple. We just intercept all NumPy calls. So when you sit and use the numerical Python, we are just going to go in and hook in and see, okay, now you're allocating an array. We'll just take that instruction and translate that into our vector bytecode. And everything was all good and well, but then we just saw that, matplotlib, you're going to plot the data, you're going to print it, you're going to directly access the data that is allocated. Well, that's not really a good thing, because we have a situation here. You are trying to directly access a contiguous memory block, which could be on a completely different node somewhere. It could be on your GPU. It might be on a completely different machine. So that was kind of an issue. And the solution to that was, and we wanted to have legacy support. We wanted to be able to take any existing NumPy application and run it without changing a single line of code and running it on our runtime system. So what we did was we intercepted the allocation calls and used memory protection, such that in the actual memory allocation we used mprotect. So when some other application uses the NumPy array and directly accesses that, it's going to throw up a seg fault. We're then going to catch that seg fault and instruct our runtime system to bring data back from the cluster such that the legacy application can access that. And in that way, we actually maintain the legacy support. Of course, there's a performance penalty in doing so, but there's still an acceleration of a lot of computations without changing a single line of code. So that was the bridge part of the system. Then we needed some engines to actually test out, if we could get some automatic optimizations out of this. And we started out by implementing a very simple engine. It does nothing else. It actually just does the same job that the NumPy C backend does, with a couple of memory allocation optimizations. And then we have the S-core engine, which does the same job, but also implements cache tiling at runtime. And then we have the M-core, which does also the memory allocation, and as well some thread level parallelization of these numerical operations on the arrays. So so far we got the idea of separating the concerns. We got a design. We tried implementing stuff, and then it was time to evaluate it. And so I've brought some data, some results. We got 4 applications, and the first application is a basic iterative Jacobi solver. And what you see here is the different engines on the x-axis, and on the y-axis we got the speed up relative to NumPy over here. So this is regular NumPy 1.6 or something like that. What we would see here is the first engine. It really doesn't do much, but it's not actually expected to do anything better than NumPy. We're actually just pleased to see that it doesn't run slower than NumPy. And then we have the cache tiling optimizations, which we're actually hoping for a lot better performance than just a 1.4x speed up. But at least, again, it's not a slowdown. And finally, we got the multi-core thread level parallelization. And on that, we got a 1.8x speed up. I should just say it doesn't really make much sense to look at these numbers without knowing what we ran them on. So this has been run on this laptop up here. And it's got 2 cores with hyperthreading or something like that. And another benchmark, which is a shallow water simulation, we're actually starting to see some much more promising results, namely that our memory allocation optimizations are actually very, very nice. We actually did nothing else but do a different implementation of some of the malloc of a memory on the arrays. And the multi-core engine over here also starts to show a nice speed up. But disappointingly enough, then the cache tiling didn't do anything for us in this particular benchmark. And a quite similar one is this synthetic stencil benchmark. We see it's basically the same workload pattern, but we see a slightly better utilization of the cache tiling implementation, and it's actually also a quite nice speed up in relation to Numpy using the thread level parallelization. And then the last benchmark we used was a k-nearest neighbor search. And here it starts to be quite impressive what you can get out optimizing your memory allocation. We get a 3.5x speed up just based on the memory allocation routines, and a nearly 7 times speed up using the thread level allocation. So that's basically where it is now. We got the idea of separating the concerns. We tried implementing that in Python Numpy by doing some tricks to preserve legacy support. And the current status is that we're not running slower than Python Numpy, and we actually got some speed ups. And currently what we're seeing with these benchmarks are that, and it's also as expected, that when you're doing data-intensive computations, then it's really the really hard part is actually utilizing your memory most efficiently. So the thing where we actually get most out of our runtime system is just the basic memory allocations, and then there's scaling for thread level parallelization. But it's really the hardest part is utilizing your memory the most efficiently. So that's basically where it is now, but it's, yeah, I'm gonna spend the next 3 years trying to make this better. Maybe it's gonna change direction, but the idea is that we really want to have the high level languages where you don't have any notion of low level details, and then we're gonna use this runtime system to parallelize it and optimize it. So the ongoing work are within these CPU engines, where we're going to add some more optimization regarding, as I said at the panel discussion, there's a lot of just-in-time stuff here as well. And by just-in-time, we mean that we can do a dependency analyzation of a set of instructions. And then instead of going to memory every time we're doing something, we can use the locality of having data in the registers. That's where you can get some very insane speed ups when you do some optimizations. We also got ongoing work on a GPU engine. We have made one implementation using CUDA. Then we got some other hardware which wasn't from NVIDIA, so we started using OpenCL and used the lessons learned from our CUDA implementation. And then we're working on the cluster engine manager, the student tie for distributing among more nodes. And that work is based on some previous work on creating a distributed version of Numpy. And then it might not be that interesting in this setting, but we're also working on a common intermediate language bridge, which makes the CPHVB runtime system available from all Microsoft languages. Now, you might not be interested in that, but remember there's IronPython using the common intermediate language. And the cool thing is really that you get automatic optimization and parallelization of your C# code, your F# code, just by using the runtime system. And lastly, we're working on a C++ bridge. So those are some of the areas we really want to improve performance by doing more engines, and we want to to solve larger problems. We're going into the clusters and more language interfaces. But we're also working a lot on actually getting this shipped out so people can use it. And we want to do our first public release. We need to decide on a license. We need to do a lot of stuff with packaging, Ubuntu packages, MSI packages for Windows, and I don't really know how you do that on Mac OS X, but there's nice ways of doing it there. And then setting up documentations on how to installing the runtime environments. So that's basically where it is, and that was it. or you can go and see the project at cphvb.bitbucket.org. Yeah.
Thank you, Simon. We've got time for a few questions. Okay, I'll lead off with a couple. One thing that I sort of noticed is that when you claim that we're not touching any code, in many ways you're just intercepting what would commonly be called from Numpy or PyOpenCL or something like that. But there's a sort of a limit to this, right? Because you have to touch everything that Numpy gets allocated for. And where is this sort of brittle, or where does this sort of break down for you? When do you notice problems with this approach?
Well, yeah, if I understand the question correctly, then the issue is really just when you have like something that you might call a legacy application, and you got a nice setup of computation that our runtime system catches, then if somebody just throws something in there which we can't handle, which ain't like the basic objects, then the entire thing falls apart, because you need to copy. Then you might have distribute everything out, but then you have to draw everything back, and it's like, yeah, that's really a deal breaker. Yeah.
Oh, go ahead, Andy.
So you said you were running these benchmarks. Is your laptop an Intel chip?
Yeah.
So I would expect just from vector instructions that you get at least a 4x performance from the time you intercept to the time you come back. If you guys had run an actual test to see if your vector code is actually getting all 4 vector units.
Yeah. So that currently when I presented the engines, our engine doesn't do anything except for those things we wrote up. We do some memory allocation, and then we do the cache tiling, and then we have the thread level parallelization. But that stuff is done, yeah, mostly like a runtime. So it doesn't have. Usually a compiler would do stuff like optimizing for SIMD instructions and stuff like that. But we don't have that there. So that's some of the things we're going to put into it.
So it's not really vectorized bytecode, it's more just C bytecode that intercepted. Because I mean, vectorized what you wrote there, like when you.
Yeah. Yeah. Okay. So, but this is what we call our intermediate language. So this is not the thing we push down to the hardware. This is what our runtime system gets and then uses to schedule down to the hardware. So it depends on what hardware you have available. Like if it's a CPU, there should be added some optimizations for vector instructions. Yeah. Yes, so that's what the M-core engine does. It tries to distribute work among the amount of cores you got. Try to look at our intermediate code and say, okay, how I'm going to schedule this down and use a shared memory architecture with multiple cores.
So, how scalable are you? Let's say you have machines that you can buy.
Exactly.
60
Yeah.
You can actually buy them.
Yeah. So we're not that scalable. Yeah, we can scale up to 8 cores, because then you, on a regular system, you start to get, especially in these memory-intensive applications, your issue isn't actually the amount of cores. The issue is the time you wait, because you quite quickly saturate your memory bandwidth. So if you got 2 memory controllers, that's usually our bottleneck, not the amount of processors, but the amount of memory controllers. And that's one of the things we're going to get into now with the thread level parallelization, is to scale this we start out by looking at the Opteron processor. It's got and we got a system now with 4 NUMA nodes, so we need to handle the non-uniform memory access in this system. And then when we got that solved and see how can we do that automatically, we're going to see it the bigger systems like the Tilera, where they got 64 cores in a grid, and then the SGI machines, and you got Intel system on a chip, and these kind of things where you got 1024, 2048 cores. So we're not there yet, but it's a goal that we should have engines to do these things, to do these low-level things, such that we can remove it from the application layer.
Okay, I think we've got time for one more question, and then we'll go to the break. We're running a little bit late. Go ahead.
You have to think more from a lazy user side. You bring
Yeah, so there are of course different ways of approaching automatic or semi-automatic optimizations. Yeah, so you got, I think the Numpy has the approach of you compile your code and then you can run an optimized version. And we're just using a slightly different approach with a runtime system where you can just inject these things into it. There are, of course, other ways of approaching the automatic parallelization approach. And we've taken this approach and we really want to see how far we can take it. Then it is a research project, so it's really about figuring out where are the boundaries for these approaches to doing these things, how are we going to approach this, and how should we try to solve it. So, yeah. Hopefully I'll be back next year and showing you some very nice numbers on how we're going to do some good stuff. Yeah.
All right. Let's thanks for having one more time.